going to look at a problem from our IMathAS online work. This is one of the later problems in Module 2 Investigation 3, and if we read the instructions, we are told that the quantities in the chart are represented by Z and W, and that those quantities are proportional. That's going to be a key idea as we are asked to complete this table. The idea that Z and W are proportional. Now if we just take a look at the two columns in the middle, this would be similar to just any T-chart or XY chart that where we list ordered pairs. So the two middle columns you can think of ordered pairs Z, W. So we need to find the value of Z that maps to negative 15.12. And if Z is negative 3.2, what's W in this relation? Here we don't know either value in the ordered pair, neither Z nor W, and then the fourth ordered pair we just need Z. Now if we just pay attention to the last two columns, then we end up with a list of W values, and we analyze the change in W from initial to a subsequent value of W. There's a change of 26.64, and there are a lot of blanks here to fill in. And we've done a lot of these W delta W charts, though we might have called them X delta X or Y delta Y, but we simply found a second value, subtracted a first value, and Y final minus Y initial would have been change in Y right here. And you can stop the video and check these values and make sure you understand how change in Y is related to this list of Y values, and then separately how these changes in M are related to these three values of M, and so forth. Okay, now if we look at the first two columns, they're just in reverse order to the charts that we've been doing in our homework. So usually we see the Y values and then change in Y, but there's no reason we can't list the Z values and place there and analyze the change in Z on the left. So back to what we're really trying to do in this video is go over this IMathAS problem, and we're given that Z and W are proportional. So that sentence says something about these middle two columns. Okay. Now if you haven't heard of the word proportionality, its definition is similar to the characteristics of a constant rate of change. You might want to take a moment, just pause the video and read through these statements. Okay, so if two quantities are related by a constant rate of change, then the changes in those given quantities are proportional. Okay, so if X and Y represent the values of the quantities, and delta X and delta Y represent the relative changes in the two quantities, then each of the following four statements is true. And I'm going to emphasize something in each statement. Let's see if I can get that. Okay. Okay. Now remember, this is our old idea. Two quantities related by a constant rate of change. Then the changes of the quantities are proportional. And that means that the change in one variable is always some constant times the change in the other variable. And we're going to call that the constant of proportionality in this case. Well, algebraically speaking, we could take this second statement, rearrange those three values into this statement, you know, if we just divide both sides by delta X. But it's another way of looking at proportionality. If change in Y and change in X are proportional, then their ratio is a constant. The third statement can kind of be summed up here. If the ratio of these changes is always constant, if we have K delta Y over K delta X, then the K's would need to cancel. Or I actually said that backwards. If this ratio is always constant, then K times delta Y would have to be K times delta X, or imply. And I'm saying that wrong, but I'll show you how to use it. Okay. So So back to our problem. Again, we're given that z and w are proportional. That's different than what we talked about here, where changes were proportional. But the description of proportionality in these three circles here we'll use with this given information, z and w are proportional. Okay, so hang on to that idea one moment. We're going to fill in some of these, some of the easier blanks. So I'm first just going to focus in on, I think what we're going to do, let's see here. Yeah, we're going to get to that in a minute. Okay, I tell you what, we'll back up and I'll talk about this again. Okay, so we're given that z and w are proportional, and if z and w are proportional, then there exists some constant, we'll call it c, such that w equals c times z. And that would mean we eventually need to find that value c, that proportionality constant. And I'll lead you through that once we fill in some of the blanks. And I found this out of one of our textbooks, and you may want to go back and you might even want to print this out and put in a z and a w. I'm gonna highlight something. Okay. If y varies with x linearly, or in our case, if z varies with x linearly, then z and w are proportional. If two quantities are in a linear relationship, then those two quantities are proportional. It is also true then that their changes, their relative changes, are proportional using the same proportionality constant. So I sum this up down here. And this is what we're going to eventually use. If y and x are proportional, then delta y and delta x are proportional using the same proportionality constant. I'm using an m here. But the reverse is not necessarily true. Okay, so if you've got a linear relationship, y equals m times x, and the y-intercept is 0, then you have the same proportionality constant for their relative changes. Okay, and that's summed up here in this slide. Okay, so I'll try to go through this a little more quickly. You can pause it at any time. If I want to fill in this first blank in the row for the column for w, I'll simply look over here and see what the change in w should have been, and I need to calculate an increase of 26.64. So we're going to add that 26.64 to this negative number, and we get a second value of w, 11.52. Okay, now using that same idea but going backwards, I can come up with the first blank in the z column. I'll look over here, and this unknown z minus 7.4 would decrease the value of z down to negative 3.2. So what value minus 7.4 would give us negative 3.2? Now you think backwards and you can get a positive 4.2 to fill in there. Okay, so right now I'm filling in some blanks by just using the changes in z to get z values, and then using changes in w to get w values. All right. So if now I think of negative 3.2 as an initial z value, I decrease that value by I decrease that value by 6.9. Delta z is negative 6.9, and that would bring the z value down to a negative 10.1. Okay. Now, since I don't have a change in w here, I don't know if I'm going to increase or decrease, or by how much to get to the next blank, so I need another strategy. And this is where we finally get to where z and w are proportional, and using that. If z and w are proportional, then w over z is going to be our proportionality constant. So off the video, I took my w value divided by the z value, and I got negative 198 over 55. My calculator showed a repeating decimal, so I knew it would be a fraction eventually. This is my proportionality constant. Then I tried again just to make sure. I took w value 11.52 and divided by the negative 3.2, and I got the same proportionality constant. So hang on to this would be our value of c, or sometimes we call it m. But we go to that third ordered pair, and I take the proportionality constant times the new value of z to get that third value of w. I'm going to let you fill that in, and then you can, then you can take this unknown value of z and solve this equation to get your fourth ordered pair. Proportionality constant times what value of z would give us a value of 5.04. Then I leave the rest of it. You can calculate those changes by just using your definition of change in z and change in w. Okay, if you want to take the time, I've put this slide in here to show a linear relationship where x and y are not proportional. And in A, the author reminds you about their changes of the variables being proportional and the proportionality constant being 5/4, but then uses a numerical approach to show you that y/x is not constant, and so the values of x and y are not proportional. It's kind of like a counterexample to the one you just did. And then if you just need to go back and think about constant rate of change and the idea of linear, I've put in this slide. You could pause and read. Thanks for your attention. I hope this has helped you with your IMathAS problem investigation 2, Module 2 Investigation 4. Thanks.